Hello and welcome to the solutions video for the Physics 20 Unit 7 unit exam. Just going to get into the test itself here. Okay. So you attach a cart with mass of 200 grams to a spring as shown below and pull it to the right. Releasing the cart, you measure its period to be 2.30 seconds. When the cart is passing through its equilibrium position, which of the following rows correctly describes its acceleration and kinetic energy? So the equilibrium position, this is the point where the spring is neither pushing it left nor right, which means there is zero force, which means there's zero acceleration. That means there's zero potential energy, so all of the energy is kinetic. So that's a zero acceleration, maximum kinetic energy position. And if you replace the cart with one that has a mass of 400 grams, the period of its motion will now be, well, the cart is on a pendulum. And the period of a pendulum on the cart is given by this equation. We know with the 200 gram cart, we have a period of 2.3 seconds. So we could go through this and solve for k, or we could find the new period in terms of the old period by saying we've doubled our mass, because that is our old period times root 2. So the most straightforward way for a new student is probably to take this top equation with 2.3 seconds for the period and 0.200 kilograms for the mass and solve for our spring constant. And then put it back in the equation to find the new period. But when we multiply it by the square root of 2, we get a 3.25. 2.6 is double the period, 1.15 is where we have it, and period does depend on mass, so it's not going to stay the same. Now, students measure the motion of a pendulum. In one experiment, they observe the pendulum as it swings 5 times and see that this takes 6.12 seconds. So the period is that 6.12 seconds divided by 5. Which in this case is 1.22. I think that's also the only question that every single student got right. And in a second experiment, students double the mass of the pendulum again, and double the mass of the pendulum and again measure the time it takes for 5 swings. Well, for a pendulum, the period is given by 2 pi root L over G. Mass is not a factor. As long as it makes no significant difference in the position of our center of mass, the mass doesn't matter. So we're going to have that same 6.12 seconds. Now here, you build the pendulum and measure its period on Earth to be 2.04 seconds. So we can actually start with the same equation. Say t squared is 4 pi squared L over G. So then G is, or L is what we're trying to solve for. Sorry. So L is G t squared over 4 pi squared. So we're 9.81 meters per second squared. Our period is 2.04 seconds. We square that. And we divide that by 4 pi squared. And we end up with 1.03 times 10 to the 0. Some of you, the most common error was to actually have a 1 here for the exponent. But if the number is just 1.03, you don't need a 1. That's a 0 because you don't have to multiply it by 10 to the anything. Now, what would the period of the pendulum be on the surface of Europa, given this mass and radius? Well, we have to find the acceleration due to gravity on Europa. So we have that g is gm over r squared. And then we substitute that into the above formula. And we find that the period is 5.57 seconds once we put this g into our 2 pi root L over g. And again, because it's just 5.57, that's 5.57 times 10 to the 0. We do have the scientific notation because depending on the random numbers, you might need 10 to the 1 here. But you need that 0 to represent it. Now, a 0.220 kilogram mass is placed on the end of a spring with a spring constant of 205 newtons per meter and a length of 50 centimeters. The mass spring system is set vibrating with an amplitude of 25 centimeters. The maximum speed of the mass during its motion is. This is a conservation of energy problem. Remember, for that we use the amplitude of the motion, not the unstretched length of the spring. So when the energy is 100% potential, it is 1/2 kx squared, where x here is our max or our amplitude. When the energy is 100% kinetic, it's 1/2 mv squared, and because energy is conserved, these two numbers will be equal. So v will be x times root k over m. Okay, so our x here is 0.25 meters. Our mass is 0.220 kg. And our spring constant k is 205. Work all that out, we get 7.63 meters per second. The frequency of the mass is motion. Well, period is 2 pi root m over k. So frequency, which is 1 over period, is 1 over 2 pi root k over m. We're given k, we're given m. So these two parts can be solved in either order. The results of the first one have no impact on the results of the second. So when we put in our k is 205 and our m is 0.220, we get 4.86 hertz. Now, our data analysis prompt. So we have our length and we have our time for 10 oscillations. We want a slope of 1 over g. That's the reciprocal of the one we used in the lab. That's going to be t squared over 4 pi squared L. Now, what's the value of g, the acceleration due to gravity? This is the one that unfortunately the entire class struggled with. That's the question that nobody got quite correct. So I'm going to do this as a spreadsheet here. So I don't think I can copy. So our length, okay, I don't need to see timelines here. We start with 1.15 and go up 0.15 each time. And then we have 21.73, 23.10, 24.40. Didn't mean to close that tab. Oh, 25.63, and our final number is 27.07. That's our time for 10. So our lengths are okay. To get our period, we have to divide that by 10. Now, keeping in mind we have to preserve our significant digits. So if on a test, it's not a big deal, right? We have a limited amount of time to do the test. You're just putting in the final result. So here I'm not picky about the significant digits, but I'll do this to model for the actual exams themselves. We have 4 significant digits here, so we should retain 4 because this number is based purely on that row, not on the rows above or below. Now, if we're doing t squared as our y, that's this number squared. And again, that display should be restricted to 4 significant digits if that's what we have to begin with. And then our 4 pi squared L is 4 times pi times pi. We can use that pi function in our calculator. And then times L. And again, this entire column should be 3 significant digits. But now here's our y, and here's our x. So when we do our LINEST, here's our y data, here's our x data. We'll do true, true, just to maintain that habit. Now this number here, some of you are putting this in directly, but we were asked for g in a linearization that makes our slope 1 over g. We have to reciprocate that. So we have a 9.19 is our acceleration due to gravity with this data. And that's the information we need to extract. And this solves our Unit 7 unit exam.